We have explored individual qubits and how they evolve. Now we face a new challenge. How do we build complex quantum systems from simpler ones? This is quantum composition, the art of combining quantum building blocks to create powerful quantum circuits and algorithms. It's like going from knowing individual musical notes to composing symphonies. But quantum composition isn't just classical composition with quantum objects. There are fundamental rules that make quantum computing radically different from anything in the classical world. First, the No-Cloning Theorem, which states you can't copy quantum information. Let's start with one of the most surprising rules in quantum mechanics. It is fundamentally impossible to create an exact replica of an arbitrary unknown quantum state. Let me be clear about what it means. You cannot build any physical quantum device that takes an unknown quantum state as input and produces two identical copies as output while preserving the original. This isn't an engineering limitation. It's a law of nature. So what does this mean for computing? In classical computing, we use fan-out operations all the time, copying bits from one register to another. You can copy classical information freely, but not in quantum computing. The no-cloning theorem forbids it. This might seem like a limitation, but it's actually what makes quantum cryptography secure. In protocols like BB84, the most famous quantum key distribution protocol, any eavesdropper trying to intercept and copy quantum states will inevitably disturb them, revealing their presence. You literally cannot steal quantum information without leaving a trace. Before we can build complex systems, we need to understand our basic components. Just as classical circuits are built from logical gates like AND, OR, and NOT gates, quantum circuits are constructed from quantum gates. The fundamental single qubit gates include the poly gates X, Y, and Z, which are rotations by pi radians around their respective axes. To the Hadamard gates, which create equal superpositions, essentially for quantum algorithms. We also have the phase gates, the ST and the general phase gate. These add phase shifts without changing probability amplitudes. Here's an elegant fact. All these gates, poly, Hadamard, and phase gates, can be expressed as special cases of rotation gates. They are all just rotations on the Bloch sphere by specific angles around specific axes. When you look at a quantum circuit diagram, it's important to understand what you're actually seeing. Unlike classical circuits, printed circuit boards, or integrated circuits with physical wires carrying electrical signals, quantum circuits are more abstract. The gates and wires aren't tangible physical entities in the same way. Here's what's really there. The qubits are physically implemented as trapped ions, superconducting circuits, etc. The control mechanisms like lasers, microwave pulses, magnetic fields are physical. The wires in the circuit diagram represent the temporal continuity of qubit states. They show time flowing from left to right. The gates denote specific transformation of these states using external controls. It's a schematic representation of how quantum states evolve over time, not a blueprint for physical circuit board. Let me give you a practical example that demonstrates the power of quantum superposition. Here's the challenge. How would you create a truly random number generator using quantum computing? In a classical computing scenario, we use pseudo-random number generator, which is a deterministic algorithm that produces sequences that look random but are actually predictable if you know the initial state. Quantum mechanics offers a genuine randomness. Here's the simplest approach. You can initialize a qubit in the ground state, gate 0, and then apply a Hardeman gate, then measure the qubit. The outcome is fundamentally random, 50% probability of getting a 0 and 50% probability of getting a 1. This isn't pseudo-random, it's nature's own coin flip. For larger random numbers, you can use multiple qubits. Want a random number between 0 and 255? Use 8 qubits, apply Hardeman gates to all of them, and measure. You get a true quantum randomness. Now we are ready to tackle multi-qubit systems. But first, we need to understand how quantum mechanics combines subsystems. In classical Newtonian mechanics, you describe interactions between subsystems with straightforward addition. In quantum mechanics, we use something different: tensor products. A tensor product, denoted by this symbol, is how we mathematically combine quantum systems. If qubit A is in state psi and qubit B is in state phi, the combined system is in state phi tensor psi. This might seem like a technicality, but it has profound consequences. Not all multi-qubit states are created equal. There's a crucial distinction. First, we have product states, which can be expressed as tensor product of individual qubit states. In a product state, each qubit has its own independent quantum state. You can describe and measure each qubit separately without affecting the other. We also have general states. Most multi-qubit states cannot be written as simple tensor products. They are superpositions of multiple product states. These general states might be entangled. Here's a key insight. In an n-qubit system where qubits are independent, which is a product state, you need just 2n complex numbers to describe the full state. 2 numbers per qubit. But if the qubits are entangled, you need up to 2 to the n complex numbers to describe the complete state. For 10 qubits, that's 1024 numbers instead of 20. For 50 qubits, it's over 1 quadrillion numbers. This exponential growth is where the power of quantum computing lies. Before we continue, I need to address something subtle about particle identity. In quantum mechanics, there's a deep distinction between fermions, which are half integer spin, and bosons, which are integer spin. Fermions follow the Pauli exclusion principle. No two fermions can occupy the same quantum state. Their combined wave function must be antisymmetric under particle exchange, expressed through Slater determinants or second quantization. Bosons can occupy the same quantum state. Their combined wave function must be symmetric under particle exchange. Anyons are quasi-particles in 2D systems that don't follow either rule. Their wave functions acquire complex phases upon exchange. Microsoft and others are investigating topological quantum computing using anionic braiding operations for fault-tolerant quantum gates. Now, here's the important point for quantum computing. Even though qubits might be based on fermions or bosons, in quantum computers, they are localized in space, trapped in specific locations. This makes them distinguishable from each other. Therefore, we can form multi-qubit states using straightforward tensor products without worrying about symmetrization or antisymmetrization. Each qubit is distinguishable by its location, even if the underlying particles are identical. But for problems in areas like quantum computational chemistry, particle identity has to be factored in. Let's talk about entanglement, which is the heart of quantum power. So what is entanglement? Entangled states are quantum states where you cannot describe one qubit independently of the others. The qubits are fundamentally correlated in ways that have no classical analog. Let's clarify some terminology. Correlated states are composite system states where the properties of one qubit are statistically linked to others. This can be either classically correlated or entangled. Classically correlated states, like classical correlations in statistical systems, if you know about one qubit, you gain information about the others, but each qubit still has its own individual quantum state. Think of it like two people, each holding one sock from the same pair. There's a correlation, but no quantum weirdness. We also have entangled states, which cannot be described by individual states for each qubit. They exhibit correlations stronger than any classical correlation and display non-local correlations that are fundamental to classical quantum information processing. Entanglement is what gives quantum computers their exponential advantage for certain problems. It's not just superposition, it's the correlation between qubits that matter. To truly understand entanglement, we need to see how it differs from classical correlation. Let's illustrate this with a machine that emits pairs of balls in opposite directions. One to Alice, one to Bob, each catching their ball. Classical correlation, 3 scenarios. In a classical domain, correlations can occur in various ways. 1. Balls with contrasting colors, which are predetermined states. The machine dispenses pairs of balls with contrasting colors that are predetermined. Alice and Bob always catch balls of opposite colors because they are arranged that way from the start. This is similar to the predetermined coin pair scenario. If a pair of coins is tossed such that when one shows heads, the other must show tails. The key point, the properties exist before observation. 2. We have gray balls with shade ink. Classical randomness. Initially, the balls contain an equal mixture of black and white pigments, appearing gray. Upon observation, the pigments flow to one ball separate, with the direction of the flow being random. As a result, one ball randomly turns black and the other turns white. In this scenario, the colors are not predetermined, and a transfer of pigment between the balls is necessary for them to assume their respective colors. The key point: physical communication or transfer is needed between the particles. Let's go to the third one. Communicating intelligent balls, which involve active coordination. Consider two balls capable of sensing their surroundings and communicating wirelessly. They can coordinate to display different colors based on the environment, like who catches them and how they are caught. The key point: active signaling creates this correlation. These examples illustrate anti-correlation, opposite outcomes. Correlation can also be direct. For instance, with fair coins, if Alice's coin shows heads, so does Bob's, and same applies for tails. Quantum entanglement, we get something fundamentally different. Now transition to the quantum realm. Consider the two balls as particles or qubits in a bare state, represented as this equation. Here, we associate the white color with state 0 and the black with state 1. When Alice measures a qubit, she employs the projection operator, this one, which collapses the Bell state to this state. Subsequently, Bob's qubit is in state 1. Likewise, if Bob measures his qubit first and observes state 0, he uses this projection operator, which collapses the Bell state to this state. At this point, Alice's qubit is in state 1. This demonstrates that the measurement outcomes of Alice and Bob are anti-correlated. However, a key difference from classical correlation lies in the quantum measurement principle. The states of individual qubits in the entangled pair are not defined until they are measured. This is shown in this figure, where balls are gray before being caught, symbolizing their undefined states. When Alice measures a qubit, she gets 0 or 1 with equal probability. But whichever she gets, Bob will always observe the opposite. This resembles the gray balls with shed ink classical scenario, except that no communication or transfer of matter is needed between the qubits. The correlations in entangled states are fundamentally different from and stronger than anything achievable with classical correlations. As you see next, they violate Bell inequalities in ways no classical system can. Let's look at the most famous entangled states, the Bell states. These 4 states form a complete basis for 2 qubits and are maximally entangled. These are the phi plus state, phi minus state, psi plus state, and psi minus state. These states were first discussed in the context of famous EPR paradox. Let's take a look at the great debate, which is the EPR paradox. In 1935, Einstein, Podolsky, and Rosen published a thought experiment arguing that quantum mechanics was incomplete. They couldn't accept that particles could be correlated in ways that seemed to require instantaneous communication across arbitrary distances. Einstein believed in 2 principles. Realism, which states that objects possess definite properties and values even when they are not being observed or measured. The moon exists even when you are not looking at it. Locality. The physical processes at one location don't depend on properties of objects at other locations that are space-like separated. Locations far enough apart that information couldn't travel between them at light speed. Together, this suggested that quantum entanglement must be explained by hidden variables, properties we simply hadn't discovered yet. In 1964, John Bell changed everything. He formulated Bell's theorem, which showed that no theory based on local hidden variable could reproduce all the predictions of quantum mechanics. Bell derived inequalities and mathematical relationships that any local hidden variable theory must satisfy. Quantum mechanics predicts violations of these inequalities. Consider a triangle with sides A, B, and C. Naturally, the sum of any 2 sides, say A plus B, is greater than the third side C. It is a geometric fact. However, the relationship A squared plus B squared is greater than C squared is not universally true. In the classical domain, if we associate probabilities with the lengths A, B, and C, the inequality A plus B greater than C represents the Bell inequality holding true. But in quantum mechanics, the linearly additive quantities are probability amplitudes instead of probabilities. Thus, when probabilities are associated with A squared, B squared, and C squared, the inequality A squared plus B squared greater than C squared showcases the potential violation of Bell inequality. Experiments have confirmed quantum mechanics is right. Bell inequalities are violated in nature. This means realism and locality must be wrong. Here's the verdict. Quantum mechanics is considered complete. It doesn't require hidden variables to fully describe physical reality within its probabilistic framework. Nature really is fundamentally probabilistic and non-local in its correlations. This brings us to a critical point that often confuses people. Even though entanglement creates instantaneous correlations across arbitrary distances, you cannot use entanglement to send information faster than light. The No-Cloning Theorem states, during the measurement of an entangled quantum state, it is fundamentally impossible for one observer to communicate information to another solely through the act of measurement. Why? Because measurement outcomes are random. When I measure my qubit from an entangled pair, I get a random result. You get a correlated random result, but I cannot control what I get, so I cannot send you a message. To see the correlation, we have to compare our results through classical means, and that is limited by the speed of light. Entanglement is weird, but it doesn't violate relativity. Nature is both quantum and relativistic, and these two frameworks coexist perfectly. So, how do we create entanglement in real quantum computers? Here are the main methods. First, we have the spontaneous parametric down conversion, the SPDC. Here we have a nonlinear crystal splitting high energy photons into pairs of entangled lower energy photons. This is widely used in quantum optics experiments. We can also have entangled atomic states. Here we are using strong van der Waals interactions between Rydberg atoms, which are atoms excited to very high energy levels with enormous electron orbits. We also have superconducting qubits. We are using microwave resonators to couple qubits. This is the technology used by IBM, Google, and others. We also have the trapped ions, which controls the motion and internal energy levels of ions held in electromagnetic traps. Highly precise and one of the leading platforms. We also have the nitrogen vacancy centers in diamond. Defect structures in diamond can hold electron spins for a remarkably long time, which can be controlled using microwave and optical pulses. We also have the quantum dots, which are tiny semiconductor structures that confine individual electrons or excitons. These can create entanglement through parametric fluorescence or spin interactions. Each method has advantages and challenges, but all exploit the same fundamental physics. Entanglement is what separates quantum computing from classical computing. It's why quantum algorithms like Shor's algorithms and Grover's algorithms work. It's essential for quantum error correction, quantum teleportation, and quantum cryptography. Understanding entanglement is about grasping what makes quantum computers fundamentally different machines that can solve problems classical computers cannot. We started with the rules, no cloning, and the mathematics of tensor products. We built up from single qubits to multi-qubit systems. We explored the nature of correlations and saw how experiments settled the deepest questions about reality itself. Now you understand not just entanglement, but why it matters and how we create it. You are ready to build complex quantum algorithms.